everyone to the YouTube channel of Infinity Learn by Shri Chaitanya, and today I am going to discuss this one last topic in alternating current chapter, and that is resonance in LCR circuit. Okay, so it's a small topic, simple things to learn from it. Okay, so let's look at. Okay, so let's take a look at it. Now concept of resonance. Now before going into the concept of resonance, students, resonance के concept में जाने से पहले एक बड़ा simple सा एक revision कर लेते हैं. What we have studied, see, like in LCR circuit we used to have an inductor, we used to have a capacitor, and we used to have a resistance. We used to have some resistance in the circuit. This was AC voltage. Let's say the current in the circuit is I equals to I naught sine of omega t. This is L, this is C, and this is R. Perfect. Now we have already studied the phasor diagrams, right, of this particular structure, this particular circuit. What was the phasor diagram? We used to say like this is peak potential drop in the resistance, this is peak potential drop in the capacitor, this is peak potential drop in the inductor, right. You know, the phasor diagram was always drawn for the peak values, right, for the amplitudes. Okay. Now one more thing, that the current was in phase with the potential drop in the resistance, or I can say that the potential drop in the resistance was in phase with the current, right. But current in the capacitive circuit leads. Okay, in the capacitive circuit current leads, that is why current is leading the voltage drop in the capacitor. Current is lagging, okay, can you see that current is lagging from the potential drop in the inductor. So these things we have already understood, that current in the capacitor leads the voltage, current in the inductor lags the voltage, or you can say voltage in the inductor leads the current, or voltage in the capacitor lags the current by 90-degree phase, right. So this is a phasor representation, okay, and we have already understood this particular thing. Still I am writing, no problem. V naught, that is the overall peak value of the potential drop in the circuit, becomes V naught R whole square plus V naught L minus V naught C whole square under root. So these things we have already studied, there is no problem, right. In the previous videos, if you are not understanding this, you can go and watch my previous videos and understand this concept, right, students. Now let's move ahead. Okay, so we will say that this is, instead of drawing the phasor of the potential drops, peak values of the potential drops, we can also draw the phasor for what? The value of the resistance and reactances. So this is what? This is what? This is XC. Everybody knows it is 1 by omega C, and this is XL. Everybody knows it is omega L, right? And after solving this phasor, we used to get the overall value of the impedance in the circuit, which used to be R square plus XL minus XC square under root, right? So we knew these things already. And after solving, what used to be the resultant? The resultant used to look like this. Okay. This, if suppose just I am taking an example, suppose if V naught L is greater than V naught C, then the resultant would be like this, and this used to be the phase difference between current and overall voltage in the circuit. Similarly, here also we can draw and say, suppose XL is greater than XC, then Z will be here and this angle will be phi. So these are few things which we have already understood in this particular chapter. Now there are three possible cases here. Number one, if V naught L is greater than V naught C, that means XL is greater than XC. In this particular circuit, voltage leads the current, right. Second possibility was there. What was the second possibility? Second possibility was this: V naught, that is peak value of potential drop in the inductor, is less than peak value of the potential drop in the capacitor, which means XL is less than XC, right, students? Okay, perfect. Now there is a third and a very amazing possibility. Now let me discuss that possibility. That is what? If V naught L is equal to V naught C. That means the potential drop in the inductor, peak value of the potential drop in the inductor and peak value of potential drop in the capacitor, if they are equal. When it is possible? When XL is equal to XC. When this happens in any LCR circuit, we say this circuit has achieved resonance. What do we say? This circuit has achieved resonance. Is it clear? So, this particular condition, here we say that current, here we say that voltage leads, and current lags, right? Here what do we say? Voltage lags and current leads. Okay, but in the last resonance condition, let me show you what will happen in the resonance condition, students. You will say, sir, during the resonance condition, because XL minus XC will become 0, so don't you think Z will become equal to R square plus 0 under root, that means Z will become equal to R, that means V naught will become equal to V naught into R. That means the final phasor will look somewhat like this. Okay, the current and the final potential drop will be in phase, right? So here we will say that in this particular condition, when the resonance occurs, we say current and voltage are in same phase. Okay, so this is the primary condition that happens during resonance. What happens? Current and voltage in the circuit, they become in same phase. Okay, they are oscillating in same phase. Okay, fine, students, is it clear? Very simple, very easy, right? Now let's look into some more nuances of this particular topic. Now understand what happens during resonance. Now what is happening during resonance? Let's try to understand that. We will say first condition during resonance is XL becomes equal to XC. That means V naught L becomes equal to V naught C. Now when this happens, this means Z becomes equal to R. Z becomes equal to R, and when this happens, we say V naught becomes equal to V naught R. Now what about current? What is happening? And plus one more thing, we say phi becomes 0. That means current and voltage are in same phase. Do you understand? One more thing, cos phi, which is known as power factor, will become 1. This is what power factor. Now let's take a look at what will happen to the peak value of the current now. Okay, now let's take a look at what will happen to the peak value of the current. Students, kindly look here, very easy. You will say, sir, current's peak value is voltage peak value upon Z. Normally what it is? Normally it is this, R square plus XL minus XC whole square. Normally it is this, but at resonance, can you see that at resonance what will happen? Suddenly this particular portion will become 0. So don't you think the value of Z will reduce? Okay, so at resonance XL minus XC, this factor becomes 0 and Z becomes equal to R. So Z is at its minimum value, which is equal to R. Can you see that? So Z gets minimized. So at resonance impedance becomes minimum. Okay, and if impedance becomes minimum, what will happen to the current? You tell me. What will happen to the current? You will say, sir, I naught is V naught by Z. So I naught will become maximum if Z becomes minimum. And what is that? You will say, sir, peak value of the current in this circuit or any circuit possible is this. So this is the maximum value of the current that you will get in the LCR circuit, which will happen during resonance. So one more condition which happens during resonance is this, that I naught becomes maximum, which is equal to V naught upon R. Are you understanding? So suddenly in the circuit what happens? The value of the impedance becomes minimum and the value of the current, peak value of the current becomes maximum. So many things are happening during resonance, as you can see, my dear students. Number 1 is this, number 2 is this, okay, that V naught is equals to V naught R. Number 3, phi becomes 0. Number 4, current and voltage are in same phase. Number 5, power factor becomes 1 or maximum, I should say. Number 6, current becomes maximum. So power factor becomes maximum, current becomes maximum. What else is left? Let's check out what will happen to the power in the circuit. Okay, we know a very nice formula. If you remember, what is the formula of power? Of average power? Average power was Vrms IRMS cos phi. Now you put the values. What is Vrms? Vrms will become IRMS upon R. That means this is maximum current into IRMS, again its maximum value, because if I naught is maximum, IRMS is also maximum, into 1, because cos phi is 1. So don't you think so, at this particular value average power consumption will also become maximum? Average power consumption or power consumption will also become maximum. Now what is IRMS? So it will become IRMS is what? I naught by root 2. Okay, IRMS I naught by root 2. So we can simply say that, 1 minute students, 1 minute. Okay. Into R into 1, okay. Vrms is equals to IRMS into R, fine. So we will say it will become IRMS maximum value whole square into R. Now this is what? This is the maximum value of the power also. So you can say it is I naught square into R by 2. So whenever they ask you what can be the maximum value of the power consumption in any circuit, you will say it will happen during resonance when impedance becomes equal to R and power becomes maximum. So consumption of the power is maximum in the circuit right now. This is the 7th point which takes place here. Okay, so these many things happen during resonance. Now, how is it possible to achieve resonance? Now let's understand that. Okay, so I hope these many points are absolutely clear, that what happens during resonance, what are the factors and how do they change. Okay, now let's try to understand how we can achieve resonance. So how resonance is achieved? How resonance is achieved? Now this is the question. Now how we will achieve it? It's a very simple concept, students. Let's see. I am saying that resonance will occur when XL is equal to XC, okay, omega L is equals to 1 by omega C. So omega square become equal to 1 by LC. So at resonance, what do we do? We do not call it omega, we call it omega naught, because this is resonant angular frequency, right? So omega naught will become 1 by root over LC. Now this is something very important, right? Now omega naught is 2 pi f naught, which will be equal to 1 by root over LC. So f naught will become equal to 1 upon 2 pi into 1 upon root over LC. Got it? So it's a very easy and simple thing to understand. So finally, students, what we will do, we will say that resonant frequency is 1 upon 2 pi root over LC. That means in any circuit, see, if you take a circuit, the value of L, the value of C and the value of R will be fixed. L, C, R, these three things will be fixed. Now if you want to achieve resonance, so what you can change is you can change the frequency of oscillation of the current or voltage, right? Now changing frequency is in your hands, right? So you can change the frequency. So once you move up to this particular frequency, what will happen? Suddenly impedance will fall down to its minimum value, current will jump up to its maximum value, power will jump up to its maximum value, and current and potential will come in phase. Okay, so these things happen suddenly when you achieve this frequency. So let's try to understand few graphs, and graphically it will be, I guess, easy to understand. Let's draw a graph of the resistance and the reactances with the frequency, right? So if I talk about what is XL, XL is omega L. So as you can see that omega is what, 2 pi f dot L. So XL is directly proportional to the value of frequency. Can you see that? XL is directly proportional to frequency, so the graph of XL will be like this. Okay. Now if I talk about XC, it will be 1 by omega C, or I should say 1 by 2 pi f into C, sorry, 2 pi f into C, right. So here XC, that is capacitive reactance, is inversely proportional to frequency. So when frequency is 0, obviously this is infinity, and when frequency is infinitely high, it will be 0. Can you see that? So this kind of graph we will have, okay, hyperbolic graph. Now what about resistance? Resistance is independent of frequency, is independent of frequency. So we can simply say resistance is this. Let's say resistance is higher. So this is your resistance, this is your XC, and this is your XL, variation with frequency, right. Now this is that particular point where the resonance occurs. Do you understand? So this is the point where the resonance occurs. Now let's understand another graph. Now let's take a look at this second graph, students. It's very simple. Okay, now draw it. Now this is the graph of impedance versus frequency. This is frequency, this is impedance. Now what is happening here, students? See, if you talk about impedance, what is the formula of impedance? Impedance formula is R square plus 2 pi FL minus 1 by 2 pi FC whole square under root, right. Now if you increase the value of f, what will happen? Again this particular parameter will rise, that means XL will rise. So overall Z will rise, right. And if you reduce f, then what will happen? Then XC, this particular parameter will rise, and while we are squaring it anyways, so this thing will rise. So we can say XL minus XC, this factor will rise if you increase f or decrease f near f naught. That means whether you increase the frequency near f naught or whether you reduce the frequency near f naught, Z is going to rise, but it will be minimum at a particular value when f is equals to f naught. So we will say the graph will somewhat be like this. Can you see that? So Z achieves a minimum when resonance occurs, and what is that minimum value? It is equal to R. I hope you have understood this graph as well. Okay. Now let's understood the final graph, which is very, very, very important here, students. So let's have a look and understand the final graph, third graph. Now this is also very important. Now this is the graph of peak value of the current with frequency. Now we all know that very well, that what is I naught? I naught is V naught by Z. So I naught will be maximum when Z is minimum. I hope you are understanding. So I naught will be maximum when Z is minimum. That means when the value of the impedance is minimum in the circuit, current will be maximum, right. Similarly, like just in the previous case we have seen, near the resonant frequency, Z was increasing only. Whether you have a frequency less than resonant frequency, Z will be greater. Whether you have a frequency greater than resonant frequency, Z will be greater again, as you can see here. So Z is always increasing near the value of resonant frequency. Can you see this in the graph? So I can say the current will be decreasing near the value of resonant frequency. That means I can say the graph of current will be somewhat like this. Can you see? This is the peak value of current which will be achieved when F is equals to F naught. This is I naught's peak value. Please don't write it I max, write it I naught max, because we are finding out the peak value of the maximum value of the peak value of current. Do you understand? We are trying to find out the maximum possible value for the peak value of the current in the LCR circuit, right? So this is something like that. So this particular point, this is termed as resonance. Now it has some importance, obviously it has some importance, that is why we are studying it. I will tell you one application of this particular concept, no worries. So I hope you understand this. Now one more thing is here, see, I naught max is equals to V naught by Z minimum, and what is Z minimum? Z minimum is equals to R, right. So if R increases, then what will happen? The value of the I naught max, the value of the the value of the I naught max peak values, maximum value will reduce. Peak value of the current, its maximum value will reduce. So we will say that if you increase R, suppose, so the graph will come like this. I am just taking example, if this is R, this is 2R, this is 3R, and so on. And if somehow you reduce R, suppose you say R by 2, suppose you say R by 2, then it will rise. So as you keep on reducing the value of R, the peak value of the current will be very high, the maximum value of the I naught will be very high, and it will show a sharp rise, it will show a sharp rise, okay, it will show a sharp rise here. I hope you are understanding this fact, this is not so difficult, okay. I hope it is clear. Now let me tell you where we can use this concept. See, this concept is used in, quickly I will tell you in 5 minutes, it is the concept used in radio tuning. So what happens in old times, now these are all electronic radios, radio tuning, what happens? We have a receiver at the radio. What is the meaning of the receiver? The receiver's job is to receive all the frequencies in the atmosphere. So right now if you are sitting in your room, or right now I am standing in the studio, all the kinds of electromagnetic waves are passing through this atmosphere. All kind of electromagnetic waves are passing through the atmosphere. But can you right now hear any song? Right now you cannot see. It's not like that. Right now the songs of the Radio Mirchi or Big FM or My FM or Red FM or Radio Mirchi, suppose it's not like that they are not playing right now. They are being played here in the form of electromagnetic waves. It's just that you need a receiver. So if we have a receiver at our end and we can receive the signal and then convert it into a audio signal, a proper audio signal, then we can hear it. Are you understanding? So this is what happens with the radio. So radio tuning, what happens? It's very simple. It's an LCR circuit and it works on the principle of resonance. It works on the principle of resonance. So here what happens? We can change the value of the resonant frequency like this. Oh, I'll tell you, don't worry. See, if I say what is resonant frequency angular wise, so you will say sir root over LC, 1 by root over LC. What is this? You will say sir it is 1 by 2 pi root over LC, I suppose. It is clear, very simple, very simple. Now, we can also change the value of the resonant frequency. It's not necessary that, suppose this value is coming out to be 100 hertz. So it's not necessary that it always comes out to be 100 hertz. I can change the value of L or C and I can make the resonant frequency 90 hertz. I can make it 500 hertz also, whatever. I can just change the value of L and C here, I can change the resonant frequency, right? Is this clear? So what are the properties of resonance? Current takes a sharp rise, power takes a sharp rise, impedance drops, becomes minimum, right? Current and voltage goes in same phase. Are these things understood? Okay, so we will use it. So let's say that we are receiving all kinds of signals. We are receiving 92.3 hertz. This is also one channel. We are receiving like 94.3 hertz. This is also some radio channel. Let's say this is R1, this is R2, and one more radio channel, not R because R corresponds to resistance. Okay, so we will say it is channel 1, channel 2, and this is channel 3, 98.3 hertz, right. So these are the frequencies at which we can hear these channels. So whenever, if we talk about a radio, radio's receiver, so the receiver is receiving all these frequencies, all these radio waves, or sorry, all these electromagnetic waves. What are these electromagnetic waves? So it is technically receiving all these electromagnetic waves right now, EMW, not BMW, it's EMW, electromagnetic waves. So it is right now receiving, this is what receiver. So right now this receiver is receiving all these frequencies, not just these three, many more frequencies, right. But we can hear only one channel. Now how is it possible? See, what happens when these frequencies comes to the receiver. Now we can tune the circuit. See, in the circuit we have a capacitor, in the circuit we have an inductor, in the circuit we have a resistance. So some things are fixed and some things can be changed. So what we do, we design the radio in such a way that while tuning, while moving the knob, in the old radios, if you remember, old radios, I am not talking about the new, these are our electronic radios, right. So in the old radio, okay, old radio, what used to happen, you used to move the knob and the distance between the capacitor plates used to change, and this is how you used to change the value of the capacitance in the circuit, and that is how you used to change the value of F naught. So you can change the value of C and you can change the value of F naught. Now what happens, suppose right now in the first case I change the value of C to C1, capacitors again matching with the channel. So let's say I change the value of C to such an extent that my resonant frequency is equal to 92.3 hertz. So what will happen, all of a sudden at 92.3 hertz, the current, peak value of the current in the circuit will rise and will become maximum. Okay. So it does not mean that you are not able to hear 94.3. See, 94.3 hertz is still there, it is also there, the current is there corresponding to this particular frequency also, but the current will take a sharp rise at near this frequency. So when you tune your radio near this frequency, then what will happen, current for this particular frequency will take a sharp rise and you will hear the audio signal of this particular frequency will be magnified, okay. And so what will happen, you will hear only the sound of this particular frequency. It's not like that these sounds are not coming, but they are overshadowed or overpowered by this particular frequency, right. Now if you somehow change it, suppose you change your resonant frequency to 98.3 hertz, then what will happen, at 98.3 hertz you will get a peak. So now you will be able to hear this audio signal properly, right. Do you understand? During both these signals you were hearing this 94.3 also you were hearing, but it was so much overshadowed that this voice was very low as compared to the voice which is coming or corresponding to this signal or this signal during these frequencies, So this becomes a resonant frequency, then this becomes a resonant frequency, right. So this is how the radio functions, right. And I'll just tell you, this is how our brain functions, right. So whatever we are perceiving right now, our brain is also nothing but a receiver and a transmitter both at the same time. We transmit certain frequencies and we receive certain frequencies. So whatever we are perceiving right now, whatever the universe which we are perceiving right now, we are perceiving only those frequencies which our brain is receiving. There are other frequencies also coming, but our brain is not resonating with those frequencies. If our brain starts resonating with other frequencies, it might be possible we might be able to experience something else. Anyways, that's far-fetched idea. So that's all for LCR circuit, okay, that is all for LCR circuits, resonance concept. It's a beautiful concept and you must have understood in today's lecture, I hope. So guys, I just have one request, subscribe to our channel, okay, support us, okay, and keep learning infinitely. That's all for today. Thank you so much. Tada, bye bye.